All right, so what happens if this field is reversed and the magnetic field, the external field's reversed? What happens? Well, now it's an any, and of course the current's just going to be pushed in the opposite direction. Okay, that's right-hand rule number one. So the magnitude of the current is going to depend on how quickly that thing moves, how large the magnetic field is as well. Okay, and of course the current, not the EMF, but the current is also dependent on the resistance of that whole circuit. Okay, so in this case it's going to be going counterclockwise. You're still using the right-hand rules. Remember, the field's going inward now, and so the force is up. The charges in the bar are making it go counterclockwise. So the direction of the force we've done with the right-hand rule. But that means, so this is going to represent what kind of force you would need to push on this, because that's the force backwards on the bar going at that particular speed. Okay, sine, as long as this is sine 90, that's a 1, of course. All right, so still the left opposite of E. So the force always opposes. So the force acting backwards on the bar always opposes the velocity, and the bar slows down. Okay, so if you were just to push that thing and not push on it anymore, well, you're still in motion, stays in motion. You're increasing the flux. That's a backwards force on this thing. Because you have a backwards force, it will slow down to a stop. Okay? Because that would be a force backwards on the thing, because we don't have that external force of the hand pushing the bar, or maybe a cat attached to it, who knows, to keep it moving. Alrighty, so to keep the bar, this is for you, get ready to answer. Keep the bar moving at the same speed, the force applied to the hand must have to, what happens to the force to keep it going at a constant speed? Has to stay the same. Okay, so you need an unbalanced or a bigger force to make it go faster, to make the thing accelerate. But the faster you go, the harder it's going to push back. But of course, the faster you go, the greater the current you induce, and the brighter the bulb. And there you go. Okay, so they're still perpendicular, just like before. So the point is, it takes an external force, because of this force backwards, to keep it going at a constant speed. So if you decrease your force, that means this force is still going to be large enough to cause it to decelerate. Or if you increase your force, that will increase the backwards force on the thing, but it will generate a greater EMF. All right, so Faraday's law of induction, that's the thing we've been talking about. And there's three things that affect that. It's the area of the loop, the magnetic field, and the angle between there. Okay, but you have to change it. Okay, so if there's no changes in any one of these three, there's no induced EMF. There's no change in area, there's no change in magnetic field, and no change in the angle. If there's no change in, that means there's no change in flux. No flux, there's no induced EMF. So here we go. So we have a solenoid. Well, that solenoid is driven by an increasing current, and a loop of wires placed around it. This red is the loop of wire. It's connected, you just can't see it going behind here. The solenoid is your blue wrapping of wire around this center thing. Why, you might say, do you have an iron core on this thing? It's a soft iron core. It makes the magnetic field stronger because you're lining up all the domains in this thing. It makes it a very powerful electromagnet. So as the current increases, well, if the current increases, what happens to the magnetic field in this solenoid? And if the magnetic field is increasing, what else is increasing? So the question is, as current increases in the solenoid, what directions induce current in the ring? Well, there's an easy way and a long way to do this. So if you think of Lenz's law, it actually makes it go pretty quick. Because you know you have an increasing magnetic field, meaning you're increasing the flux through this loop. So according to Lenz's law, the current's going to be induced in this ring to oppose a change in flux. So first of all, find out where your north pole is on this thing. So the current's wrapping around this way. This is your last right-hand rule to find the north pole of a coil of wire, where your hand wraps around the front side around to the back side. The north pole is upward. And that means you have an increasing north pole on top. Well, to oppose that increasing north pole, you have to fight back with a north pole going down. So if you fight back with the north pole going down, that means it opposes the current's induced in the ring. It's induced in the ring to oppose a change in that flux. That must mean the induced current must be going in the hand in the opposite direction, which in this case is clockwise. So it's going to be the opposite of the solenoid. Okay, so what happens is, so I'll do it a little bit slower. Okay, there's a lot going on in here. So you have the magnetic field is increasing this way. So to oppose an increase in that, you're going to reverse that north pole. So the north pole is going to be opposing that increase of the pole on that loop there. And so the EMF will create an opposite B field, which is downwards, to oppose that increase in flux, to try to cancel out that extra flux. And that to cancel out extra flux, that must mean using the right-hand rule, the very last one, the right-hand rule for solenoid, even though I'm using it on the, not the solenoid, but I'm using the loop of a wire, it's the same idea. That means that the field is actually downward, meaning it's going in the clockwise direction. That's the use of that. So Lenz's law makes understanding what direction the induced current is going very quickly. Faraday's law helps tell you how much the induced voltage is, but Lenz's law tells you exactly what direction it is. Okay? Alrighty. So, in this case, solenoid is driven by an increase in current. The loop of wire is placed around it. Recall the loop behaves like a bar magnet. Opposite currents, polarity. So this is the bar magnet of the solenoid. Well, to oppose an increase in current, you have to have another magnet that opposes that change. So to oppose that change, it's got to go in that direction. So what happens when the loop has less resistance? Well, if this loop has less resistance, is that more current or less current? That's more current. Exactly. That is more current because there's less resistance. And more current means a greater opposition. Okay? But, so what happens when the loop has less resistance? Well, you're still going to have the same EMF. Okay? So if you have less resistance, you're going to have more current. So that keeps the EMF actually the same. So you'll have a more current going through the thing, but you have the same EMF. Okay, another question here. Oh, there you go. We just did that. So what happens if the loop is broken? What if there's no contact in between there? Well, what's the flow if there's a current's broken? That means there is no flow, so there is no induced current because it can't go in a circle because there's an incomplete circuit there. Okay, so there's no induced magnetic field because it can't go in a circle. Alrighty, so there's your north pole, and then you don't have an opposition because there's no current going to there, so there's no induced whatsoever. Alrighty, so which way is the magnet moving if it is inducing current and the loop is shown here? So we're dropping a magnet here. Oh, we don't know we're dropping a magnet, do we? Which way is the magnet moving? Is it going up or down? Here's what we know. The current goes this way. So how do you know which way this magnet must be moving? Well, that's Lenz's law. Lenz's law, you're always going to use that last law where the fingers wrap in the direction the current goes and the thumb points to the North Pole. So since that's going counterclockwise, as I wrap my hand around that thing, wrapping my hand around it like this, that means by Lenz's law, the induced current in the yellow solenoid makes the North Pole up. That opposes the motion. That means that magnet is falling, because it wants to oppose an increase. As that thing gets close to the loop, you're going to get more and more flux because it's more concentrated near here, less concentrated out here. So to oppose that increase in flux, you fight back with the North Pole up. That means the current's going in the direction that it's showing. So that means the magnet is indeed going down, down, down in that burning ring of fire. Thanks, Johnny Cash. So that's just what I just said. Okay? Give you some time to read. Okay, so there's the North Pole that opposes that change in motion. So if I reduce the resistance in the wire, will it go faster or slower? Well, remember, reduced resistance means maybe the same EMF, maybe, but that could change if it's going faster or slower. But that means less resistance means more current. More current means bigger magnetic field. Bigger magnetic field means it actually goes slower. So the better conductor it is, the slower it would drop through there. In fact, if you would make this into superconductor, you could have so much current flowing because the resistance is so low, it's enough to make that thing float. Okay? Because you'd make a strong enough magnetic field that opposes the change and it wouldn't go anywhere. Okay? So there you go. Alrighty, so a few more examples here before we wrap this up in 4.5 minutes or less. So the conducting loop is inside the solenoid. So we have a conducting loop inside of a solenoid. This is the solenoid over here with the current going in this direction. Okay, so if the current's going in that direction, this is how I'd find the magnetic field inside the solenoid. It's a permittivity of free space, permeability of free space, the number loops. And that's the flow of current. So that's not changing. So I have a constant field, doesn't matter where it is, and you're a constant magnetic field. What happens to the flux of the loop when you increase the area? All right, so if you increase the area of the solenoid, how does increasing the area change the field? Oh, it doesn't. So if I don't change the field, how does that change the flux? I didn't change the area of the loop. I'm just changing the solenoid, not the area of the loop. So how does it change? Wait for it. It doesn't. Because by making it larger, you're sure you have a larger area of the solenoid. Technically, that would add more wire and more resistance, which might make the current fall. But if we're keeping the current the same, theoretically, we still have the same field throughout the whole thing. So that theoretically doesn't change. Doesn't change the flux, therefore doesn't induce an EMF on that loop. Okay. What if you increase the, oh man, cat's out of the bag. So I keep this the same, but I increase the area of the loop. Well, that's a greater flux. So if you increase the flux, well, then that means, so here's the thing, so if the current's going this way, that means there's a north pole coming right at your face from the solenoid. That's the right-hand rule we've been using for lenz. Coming right at your face. Well, that means this has to be just the opposite, because it's going to oppose that increase, so the current's going to go in the other direction of that. So if you increase the area, you have an increase in flux, which means now you're inducing an EMF, and it's going to cause the current to go in the other direction. How about if you increase the current in the solenoid? Well, that means it's a stronger field. You increase in the flux, you're doing the exact same thing. So you're still increasing the amount of flux into there by having a stronger field. Current goes that way. What if you rotate it slightly? Well, if you go clockwise or counterclockwise, it doesn't change the flux. But if you rotate it on end one way or the other, that makes it less. So if you have less flux, well, then it's going to be just the opposite. It's going to want to oppose a change. It doesn't want less, so it's going to try to keep it the same. So the only way to keep it the same, the current has to be induced in the same direction. So by rotating it to a smaller area, it's going to induce the current to go the other direction to try to stabilize or keep the north pole going right at your face, and it's going to actually go in the opposite direction. Alrighty. So solenoid inside a conducting loop. And so now the solenoid's on the inside. This is loop on the outside. So if you increase the area of the solenoid, loop and all that other stuff. Whoops, okay, so there is the direction on the solenoid. What if you increase the area of the solenoid? If you increase the area of the solenoid, well, now we have the same field but a greater area. A greater area means we have a greater flux, so that's going to increase it and make it go backwards to oppose that increase. What if you increase the area of the loop? Well, if you increase the area of the loop, you're not gaining or losing any more flux as this outside thing gets larger, so nothing happens. What if you increase the current? Well, that's more flux, so once again, that's going to cause it to the back EMF to go exactly the backwards direction. Alrighty, so there it is, guys. There's a sum of everything. 30 seconds here you got to memorize everything. Gonna make sure that's the last slide here. Yep, it is. So there's your Faraday's law. Lenz's law it's not really a mathematical thing necessarily. It's from Faraday's, but it's how you would find the direction of things. So by changing the area, the field, of that, they all three change the flux and thereby inducing an EMF. All right. Have a wonderful time. That could be it for this week.